so let's talk about work. Now, it's sad, but physics' definition of work is not your definition of work. Remember, physics is all about getting things accomplished, and if you don't, then you don't really do anything in physics. So work is when you have a constant force and it accomplishes a movement or displacement, okay? So you not only have to apply a force, it's got to do something. It's got to be effective, okay? And so here's our formula. It says W equals F times D, quite straightforward. What do those little lines there represent? Parallel, not two. It's okay. That's supposed to be parallel. So this is not only just a force, but the force has to be in the direction or parallel to the displacement, okay? It can't be this way while you're moving this way, all right? So force parallel to the D, okay? And the D is really displacement. We tend not to use delta X. You think you should. I can't even spell displacement, which pretty much is distance traveled. Okay? Of course, this is in meters, and of course, this is in newtons. Okay? Now, what if your force is not in the direction of your displacement? What if it's at some angle, which we love in physics? Yeah. That it turns out that you can substitute F parallel with F cosine angle, because you're trying to find the X, like if this is in the X direction, this would be the force that would be in the X direction. All right? Does that make sense? All right. So this, turns it into the X component of force. Okay? Trying to make these two in the same direction. Okay. And as we realize, if you have a 90 degrees, what's the cosine of 90? 1 or 0? 0. So if you apply a force like this, but try to move, but are moving like this force is do you realize that force is not accomplishing that movement? Right? So you are not doing work like that. That's no work. Work turns out to be 0. Okay. So let's look at some examples. So if you have are pushing a box on a carpet at constant velocity, right, what do we think? Then we do have a force that's causing the displacement. Because if you stop pushing, it'll stop moving, right? Okay. If you're carrying a box of food, all right, down the hall, then there's a problem. And the problem is, if you're carrying this box, which way is your force? Up. And so I know you're moving forward, but we're not speeding up forward, and we're going to constant. There is a little bit of friction against the ground to move you forward, but most of your foot motion and most of your force is up. And if that's not causing this, right, then our work is 0 or close to 0, right, because your force is up and your D is forward. Okay? All right. So that's a problem. So you got a D, but the force didn't cause the D. What about standing, holding your heavy backpack? You get tired doing that, right? But getting tired is not the definition in physics of getting work done, right? So the problem is, once again, this case you have a force, right? But your displacement is 0. So, right, no work done. All right. It's not fun, but just because you're not having fun doesn't mean you're doing work. All right? Okay. So here is that wonderful picture we were really relating our formula to, that if you pull at an angle like this, then this angle, right, if you're given this force, we really have to find this force, right, which created that formula. Okay. Units. Units. What do we do? Well, we know our units for force. And we know our units for distance, I hope. So we have a Newton. And we have a meter. And anyone know what the SI unit for Newtons times meters would be? Yes?
A joule?
Yes! It's a joule. Okay, which is a capital J. All right. Anyone know the British unit? Woo! Foot-pounds. All right. He might have cheated by looking under there. All right, 1 joule equals 0.738 foot-pounds. All right. Do you see why it would be foot-pounds? Right? Foot, they do it backwards, right? So the foot would be the distance and the pound would be the force. Yeah? They don't say pound-foot. Okay. All right, let's try a problem. We have a crate. It's pulled. Well, apparently I changed my numbers. That's 40. I don't know. So we have a crate, and we're going to pull it. Whoops. What angle? 100 newtons. We're going to, the displacement is 40 meters. Okay. And I know the force of friction is 50 newtons. And this angle is 37 degrees. All right. So what are we going to do? Well, I want to find the work done by each force, and the net work done. Okay? So the first thing I'm going to do is find out the work done by the pull. Whoever's doing the pulling, by some person. Okay? And I'm going to do F times D, but I can't, that F parallel, right, I'm going to have to do, right, 100 times cosine of 37 times 40. Okay? All right. I changed my numbers, so now I don't know I have the answer. So I actually have to pick up a calculator. Oh, my cosine didn't change, though. 37. So we have 100 times 0.799 times 40. And if I do that, I have 100 times 40. All right, 3196 Newton meter. Oh, let me just make it I was going to make it Newton meters, but I can say joules. Okay. Who else is doing work? Mr. Friction. And we're going to do F times D again. And so what do we have now? I have 50, maybe.
Negative 50.
Ah, I like that. All right? It's going the other way. So we have negative 50, right? And I don't need cosine. I could, well, you know what I could have done? I could have done 50 cosine 180, right? And then I would get negative 1, and it's all the same. Yes? Okay. All right. So if you want 50 cosine 180, that makes some people feel better. All right, what do we get here?
Negative 1,000. How was that?
Someone said 90.
Yeah.
Okay. All right. So what's my network? What do I do there? So what do I got? No, positive. 1196. I don't know. I don't know how many sig figs. We really, so what, like 1200? There we go. I think we only had up to here, and then the rule of addition, blah, blah, blah. Okay. Huh. Why do I have a network? Do you think they should all cancel out?
There's displacement.
Not just movement. That's not a good enough answer.
There's displacement.
There's an acceleration.
Oh, there wasn't. We did too much work. Do you agree? You did more work than you had to do. Right? You did more work than you had to do. So, I heard it over there. If you did more work, it didn't just move. You made it accelerate. We did extra work. Okay? And it can't be wasted. So that extra work, right, will cause an acceleration, which we'll deal with later. We'll figure out a way how we can turn that energy into movement. We're not there yet. Okay? But you can see what the options are now. Yes? All right. Are you getting excited about all this work? Woo! Yeah. It's going to take work to do work.
Yeah.
I'd say so.
I didn't get it. I'm just like, what happened?
So I haven't learned this unit yet. I don't get the joke.
All right. Oh, look, we got an incline.
Yeah.
That's our favorite.
I'm just gonna be in here.
You will be happy. He's just hiding. You know what? Just give me like 2 minutes and I'll make you happy about this. This is one of the rare times it comes out like for the better. Okay. So, all right. I got Ransom here and he's going to be climbing. He's a little hiker. There we go. All right. He's going to go climbing up the hill. And I want to know how much work he's going to be carrying this 15-kilogram backpack. And he's going up 1,800 meters up a 1,000-meter hill or mountain, if you want to call it that. And he's at an incline at 25 degrees. And so, whoa, we got it's not nice, is it? You know what's not nice? So first of all, what's not nice is he's going this way. It's up a hill, but it's not up. And, well, we know this would be our D, yeah, in a sense. But is your force that way? If you're holding up a backpack, his force is which way?
Oh.
No, gravity says, I'm holding this down.
Yes, you have to
So the person has to do this upward, yeah? So the person has to apply a force equal to the weight of the pack to be able to get it up the hill. Okay. Now let's bring out our friend cosine. Because, first of all, if this is our force direction, and this is our D direction, don't we need the angle between the force and displacement for the little worky formula we just did? Okay. Well, do you remember your rules of angles? You love this. Remember your alternate interior angles? Do you know this? That's this. Yeah? Okay. Stick with me. It's going to get better. All right. So, it may have been. All right. I got to talk faster. Okay. Cosine is what? Isn't cosine adjacent over hypotenuse? And what's my adjacent?
Height.
And this is my D, right? Yeah. So my height and my D. So if I solve for height equals cosine, I just want to cosine angle times D. Yes? Okay. Didn't we just learn on the page before that work equaled F cosine angle D? Watch the magic. Isn't this, and isn't that the height? Can't I just replace height with cosine angle D? It's going to get better. What force did I say we had to apply? Just the weight. So how much work does it take to carry the backpack up the hill? All you need to know is mgh. All of that crap goes away. And we get mgh. What does that mean? Why is this important? What matters and what doesn't matter?
The angle.
The angle doesn't matter. What else doesn't matter? The distance you went. And the speed doesn't matter as long as you don't accelerate and as long as there's no friction. No, like, resistance to your motion. Okay? Really, really interesting there. So, the work does not depend on the angle of the hill, only the height of the hill. Do you remember what I said on the first page? Physics is really, really straightforward. All that matters is what you get accomplished. And what are you getting accomplished here? You're getting it up the hill. It doesn't matter how you get it up the hill. It doesn't matter how you get it. If you get it up the hill, you get the same work done. So let's look at these three pictures. Okay? Let's say your options to get to the third floor, or just the second floor. Third floor, that would be a big ramp. But let's say get upstairs. You could take a ramp, or you're at the mall, right? Do you take the ramp? Do you take the stairs? Or should you take a ladder? We're going to install one of those somewhere by a catwalk.
Where's the ladders at a mall?
There.
I feel like that would be very elevated.
It shouldn't matter. Okay, right? But there's a difference, because what do most people take when you're kind of chill and tired? What do you take?
The ladder.
The ladder. You take the ramp. Why do you want to take the ramp?
You don't have to lift. You can slide your feet.
Okay, you could slide your feet. Well, you know, in a sense, right? You don't have to do this big step at a time, right? You could do little. And in fact, what did you do? You spread it out. What did you spread out?
The work.
You spread out the work. Did you get rid of work?
No.
You gotta do it. You're doing it slow. You're doing it slow. Who takes the ramp? Grandma. Because she can do it, but she has to do it slow. Right? She's never gonna be able to do that. Right? Because this is all at once. Right? This is a little more gentle. Baby steps, big steps. You know, and if you really got it, what do? You can jump. Just do it all, right? It's all the same work. Guess what? It's not the same. Some people a little understanding this. You had to jump. What does it take to jump?
A lot of force.
No. A lot of force in a short period of time. There's a name for that. It's power. Right? Same thing with cars. Right? Some cars can't go up, too steep of a hill, right? It's going to be trouble. The on-ramp, and do you ever, right, some like Jackson Road, that on-ramp, that's uphill on-ramp. You always get in the left-hand lane because you got some big truck or some little Fiesta that can't go uphill and accelerate at the same time, right? And they get on at like 40 miles an hour, it doesn't work out, okay? So you don't want to have to do too much. So the less, the more you spread out the work, right? You can do it like this. You can do it from back here. That would be even less work. Less power, same work. Okay.
Would least work be a flat surface?
The elevator would be no work.
No, would the least work
The
be a
elevator
flat
would be
surface?
working. I'm sorry, what?
But then you
Least
don't
work
go
be a
in the
flat
inside.
surface?
But then you're
Then you're not doing work.
Okay, yeah, it's a flat
How's
surface.
that?
So water.
If you didn't go up the hill and there's no friction, you didn't do work. Unless there's another situation, which is bam.
Okay, in a frictionless environment, it doesn't take work to move horizontally.
If you're not shoving something forward or dragging it in the direction of motion, you're really not doing work. You could argue because you're walking and you're pushing back to push yourself forward, there is some, but you realize most of what you're doing is this, right? Aren't you wasting a lot? Right? If you had a skateboard, right? Don't you push off once and then just keep moving? You're not doing any work. Okay? All right, kinetic energy. So I know you've had a little bit of this. Kinetic energy is the ability, first of all, energy is the ability to do work. Kinetic energy is energy of what? Motion. And if you have something with this kinetic energy, it has the ability to do work on something. Okay? It has the ability to do work on. Oh, you know what? Right? You got a big car, and it's going down the road, and it has a lot of kinetic energy, energy of motion. Do you jump out in front of it? No, because it could do an FD to you, right? Apply a force and give you a displacement, right? It's going to do work on you. So just keep that in mind, right? So let's come up with another formula. You're going to, well, I don't know if you're going to like it, but actually, I think it's going to make you mad. Watch.
Whoa there.
Work. We said work, and I'm going to put net, because the net work you have left over is with a net force times V. Didn't we say F net equals MA? So can I put MA in for F net?
Yep.
So work makes you mad. All right. There we go.
I get it.
Get out of here with your bad puns.
All right. You remember this one? This is a while ago. V final squared minus V initial squared plus 2AD, or delta x. So that's our displacement. I rearrange this and solve this for A. So I get V final squared minus V initial squared over 2D. And guess what I want to do? Yeah. Right, for that, which goes there. So let me write that out. So we have VF squared minus V initial squared over 2D. And do you see what happens? D goes away. And we don't leave it junky like this. We normally separate it. So do you see we got a divide by 2? So we get 1/2, distribute the m, mv final squared minus 1/2 mv initial squared. Only the v's are squared, not the whole quantity. Okay, only the v's are squared. All right. So work, the net work done on an object, can be the final velocity squared times the mass times 1/2 minus the initial. Final minus initial, which is normal. It is the net work. So do you realize normally in a problem, if you have an object and it changes energy, do you think normally the mass changes? If you got a car and you want to change its energy, you don't change it by its, like, part of it doesn't pop off or add to it, right? Okay, door doesn't come off, and So normally it's just the velocities that are changing. And kinetic energy, by the way, is this: 1/2 mv squared. So basically what we're saying is that the net work done on an object is the change in kinetic energy. Okay? Which is a work energy principle. The change in kinetic work can cause a change in kinetic energy. Didn't we see that in the first problem when we were pushing a box and we pushed it too much, we had leftover work? What that work going to do? It's going to do this, right there. It was going to change the energy. And if we knew the mass of it, and we knew how much net work we had, we could figure out the change in its velocity. Yeah? Which is kind of cool. All right. All right, there's kinetic energy. Guess what's next? Potential energy. Again, you know something about potential energy. You're going to be happy because this is all going to get full circle in a second. So potential energy is stored energy. Now, most people only think of, like, your only example ever, guys, it is a ball, and if it has kinetic energy, it's doing what? It's rolling. And if it has potential energy, it's what? It's on top of a hill. Okay? And that can work. But we have different kinds of stored energy. It has to do with energy of position. So the common one, like we just said, would be called gravitational potential energy. So this would be a ball or a boulder on a hill. Okay? Where it has the ability to do work. Right? What if I held a bowling ball over your head? Would you be worried?
Yeah.
Because it has the ability, once again, to do work on you. Or I could throw a bowling ball at you with a speed. It would have kinetic energy. You'd be worried about that. Okay? The kinetic potential energy. And so that really is a position relative to the Earth. Okay? We had a ball. And like a raised hammer has the ability to do work, or a ball on a hill, or a boulder up high. And guess what? It all comes down to this. Didn't we see this already? MGH. You know why? Because we said before work was MGH. But if you take energy and put a ball up high, how much energy does it have? The amount you just gave it by putting it up there. Does that make sense? I stored that energy. I took my energy and lifted something up, and that's now stored energy. Okay? Yeah? All right? All right. Where should you measure the height from?
The Earth's radius.
How about this? It doesn't matter. Because you know what? It's relative. It's very relative. Because, normally we don't want to know PE. Normally we want to know the change in PE. Because the change in PE is related to work. I just said I had to lift something up. Do I really care where it started? Nope. Do I care where it ended up? Nope. All I need to know is how much I raised it. Right? I just need the height at which you changed it. So I really need the change in height. That's really what I care about. Yes, you can assign something potential. And that's if I'm going to find, delta PE. So normally we don't care just about an individual potential energy. We want to compare it to something, like if I said a ball is sitting at a height of 50 feet, does that mean it has potential to do something? Maybe, maybe not. Maybe this is 50 feet in elevation above sea level, and it's sitting between two hills that are 100 feet. Right? It's all relative. Right? If I dig a hole right here, now, right, it's got some potential to do something. So it's all relative. Okay. Now, tomorrow we're doing a lab. We're not dropping balls on people's heads. Maybe later. All right. So we're going to do potential energy in a spring. So we can store energy in a spring. We can do it two ways. You can compress a spring and store energy in it. Because here's how you know you stored energy in it. Doesn't it take work to squeeze the spring? Aren't you forcing it a distance? Now you've stored energy. That is work. Okay. If you stretch a spring, don't you have to do the same thing? Or an elastic or a rubber band. Same thing, right? Right? This is why you worry if someone stretched a rubber band and put it close to your face. Right? Because you know there's stored energy in it. Right? Okay? And the stronger the rubber band, the more you've stored, right? The harder it is to pull it back, the more work and energy. Okay. So here's our formula. It's just what I said. So this is the force of the spring. X, guess what X is?
Distance.
That's our distance, or our displacement. This is how much we're going to stretch our spring. Okay? Depending on the units, we can use meters. You could use centimeters, depending on your constant. K is a constant. What kind of constant? It's a really technical name. It's called a spring constant. Okay. What do we know about the spring constant? The higher the constant?
It doesn't happen in the closer to the spring.
The what? I sometimes say that it tells you the springiness of the spring. The higher the K, the more force to do the same stretch. So if you stretch it a certain amount, the bigger this K is, the more force. Okay, so the higher the K, the greater the force to stretch, and that really means the stiffer the spring. Yeah? The greater the stiffness, I don't know. Okay. Can you get that? Why is there a negative sign there? This is annoying.
Is it because you compress the spring?
No, it's because the spring is pulling this way. But you are pulling, displacing the spring this way. Yeah? So the problem is, guess what? You're going to be pulling on this and measuring how much you're pulling, and it's in the opposite direction that the spring is pulling back. Sometimes you'll see this formula with a negative, sometimes not, depending on is this the force of the spring, or is this the force of the person pulling on the spring? Yes? Because they're in opposite directions. Okay? So I can say F of pull, and this is F of spring. Okay. So that's what we're going to be measuring. You're going to have to find the K, or spring constant, of a spring tomorrow. The other thing is we have a formula. This is interesting. And this is the formula for the potential energy in a spring. Okay? Look at that. What does it look like? To me, it looks like something. What formula did we just have that was mirroring? Kind of looks like the kinetic energy formula, 1/2 mv squared. Except for this is 1/2 kf squared. All right? And actually, I need to talk about both of those. So here's what's interesting. If you have double the pull in your spring, so you pull the spring some amount, okay? If you pull double that distance, what can you tell me about the energy stored? Is it double? 4 times. Okay. All right, that's kind of a surprise. Let's talk about kinetic energy and you're driving a car, and like it's kind of slippery this morning, right? It's a little slippery, and you go, what's the difference? If I go, if I'm going 20 miles per hour, 40 miles per hour, they're both pretty slow. What's the difference between going 40 miles per hour and 20 miles per hour? You're going twice as fast. How much kinetic energy are you carrying? 4 times as much energy. Tell me about if you hit something going 40 instead of 20. How much are you going to get hurt? 4 times as much. How much damage are you going to do to your car? 4 times as much. What if you go 60 instead of 20?
8.
Right? It's 3 times faster. Squared is 9 times the energy you're carrying. Guess how much it takes to stop?
9 times.
And what if it's slipperier? Then it's never. Okay? So, think about these things. You carry way more kinetic energy as you increase in speed because of that v squared. There's a lot of squares in physics. Okay? All right. Last concept here. Conservative versus non-conservative forces. So, normally, in the ideal world, the path taken doesn't matter to determine the amount of work done. Remember we said ladder, ramp, stairs, it's all the same as long as you get the same thing accomplished. For gravity, for spring, electric forces, this is all true. There's a problem, however, that work or energy is not conserved, and you probably can figure this out, and path does matter if friction is involved. Okay? And also if there's some problems with like tension in a cord can be a non-conservative case. But let's talk about friction. The deal is, if there is friction, then path taken does matter. Because the path with a lot of distance will be a lot of friction, right? Right? So then the long ramp is worse to do if you have a lot of friction, right, than lifting it. Because if you lift it, first of all, you have less, right, less Fn in there, and so things get kind of wacky. But if you don't have friction, then with the path taken does not matter. All right. Last thing, now that we've talked about, mentioned the word conservation. Okay? Conservation of mechanical energy. By the way, mechanical energy, we're talking about kinetic and potential energy, spring motion. We're not talking about chemical energy or electrical energy at this point. Okay? If we have only conservative forces, the total mechanical energy of a system neither increases or decreases. That means the change in kinetic energy plus the change in potential energy equals 0. So overall, so if, let's say, you have a ball at the top of a hill and it was at rest, right? It had no kinetic energy and all potential energy. As it starts rolling down the hill, it gains speed, doesn't it? But as it gains speed, what does it lose? It loses height and potential energy. And when it gets at the bottom of the hill, it has no potential energy, it's all kinetic. Guess what? You know all the problems in chapter 2 that we did with like a falling ball, and we find out the velocity at the bottom, all that? We can use these formulas now. We don't have to use our old formulas. We can know, if we know mgh at the top, and there's nothing else going on, it should equal 1/2 mv squared at the bottom. Okay? We don't care about all this other stuff going on. We can just use that. Okay? We could also say KE1 plus PE1 initial equals KE plus PE. There is no loss. And here I have the little skateboarder jumping. Off the top, he's got 3,000 joules of potential energy. As he falls, this decreases, KE grows, until finally he's all kinetic energy. Here we have another case. There's a skier, all PE at the top, right? Reduces. We don't really care at some height. So all it is just a comparison here. So we measured from some ground level. You could use anything at your ground level. You'll get it to turn out the same. And so we can see more kinetic than potential at this point. If they jump, how high do they go? Right? It all comes all to the potential and kinetic energy here. And here we see that at the bottom, all PE. All KE and no PE. Okay? And overall, everywhere, 50-50-50 is the total. Okay? So what's interesting is any point, do you realize you can calculate the velocity? Because if you know the height here, so we can just solve, we know this much, set it equal to 1/2 mv squared. Right? If you knew the PE and you knew the total at first, you could have found out this 35, again, set equal to 1/2 mv squared. Everywhere you can set it equal to 1/2 mv squared. Okay? All right. Okay, so you are armed. We're going to wait with power, because we're not going to do power until after Christmas break. Okay? You can skip.